Hello everyone, it is time for the Unit 7 FRQs. One long FRQ, one short FRQ. You get 32 minutes to do both of them. I felt like those MCQs were a little bit challenging, but we ride, and we continue on with these FRQs. So let's get into it. Answer the following questions about C2H4O. I almost forgot to read that bolded portion at the beginning that says I have to show work to get credit. Oh, I'm gonna show my work now because it says that you must show work to receive credit. Okay, so this molecule is a gas at room temperature and can be harmful at concentrations above that. What is the maximum mass of this compound that can be safely present in a room with a volume of that? So let's go to moles. Molarity equals moles over liters. We are at the portion of the year where you should really be ready and willing to convert using the molarity equation or the dilution equation. Let's get to moles of this compound. So if we have this concentration, 8.17 times 10 to the negative 6. Let's find out how many moles in 3.00 times 10 to the 5th liters. Converting to moles, we get 8.17 times 10 to the negative 6 times 3 times 10 to the 5th. 2.451 moles. We're not done yet, so that's the amount of moles that we can have based off of that concentration and that volume. Let's convert that to grams by using the molar mass that they provide. So 1 mole is 44.06 grams. And then so that number we got times 44.06. Rounded to 3 sig figs, because it looks like all of these 3 sig figs, 3 sig figs, 4 sig figs, and we get 108 grams of the C2H4O. Two structures, X and Z, with the molecular formula C2H4O are shown in the table. Based on Vesper theory, predict the HCH bond angle in structure X. All right, in structure X, let's find HCH. So we have an H, a C, and H. So it's really talking about this central atom. What is the bond angle? It's we have 4 domains, tetrahedral. That is a bond angle of 109.5 degrees. We like Vesper questions because Vesper questions are pretty straightforward. It's either you know them or you don't, and I hope you know them. 109.5 degrees. A student incorrectly claims that X and Z are resonant structures of each other. Explain why the student's claim is incorrect. Resonance has to do with when there is a double bond or a triple bond that were on one element that could easily be swapped to another of the same element. The reason that these are not in resonance is because they're just entirely different structures. We have a whole extra H on this, or we have a whole, oh, no, we don't have an extra H, but we're swapping like what it's actually bonded with. These are entirely different structures. So in resonance structures, it has to do with the connectivity of the elements are the same, not just, what I said, the connectivity of the elements must be the same. In these two structures, I have an O. This H is attached to an O, where I don't have an H attached to O in this one. So just different structures. So in resonance, I'll just say the skeleton of the structures must be the same. Okay. X and Z are both gases at room temperature at 1 atm, and they react according to the following equation. X yields Z. Write the expression for the equilibrium constant Kp in terms of partial pressures of X and Z. Be careful here. If it's asking for a Kp, it needs to be in terms of pressure. Usually these expressions are in terms of concentration, but this is really the one exception. Kp is going to be equal to the partial pressure of Z divided by the partial pressure of X. If you do not put the partial pressures there and you put concentration instead, it's wrong because they asked for partial pressures because they asked for a Kp expression. For the reaction represented above, the value of the equilibrium constant is that which would have the greatest partial pressure at equilibrium, the reactant X or the product Z. Circle the option and justify your choice. So this is a really, really, really small Kp. Okay, another way to think about Kp is products over reactants, and I guess this does a pretty good job. If that Kp is really small, that means I should have significantly more of X than I do of Z, because if the partial pressure of X is way bigger and the denominator is way bigger than the numerator, that would lead K to be a very, very, very small number. So the partial pressure of X is going to be greater. This is my option. And we're going to justify that by saying the equilibrium constant Kp is very small. Meaning the denominator, which is the partial pressure of X, must be way greater than the numerator, which is Py. An empty vessel is filled with compound X and sealed shut. The initial pressure of compound X is 0.55 atm. Calculate the partial pressure of compound Z in the vessel after the equilibrium is established and held at a constant temperature. All right, so we're given an initial pressure, and we're trying to find the equilibrium pressures. So this is going to be a Rice table, RICE. The reaction is pretty simple. It's just X turns into Z. So we're going to write X, Z up here for equilibrium. We have 0.55 atm of X, and we don't have anything of Z. X is going to go down as Z goes up. It's kind of awkward to use X as my variable here, so let me just pick a different variable. We'll go with N, so minus N and plus N, and then we're going to get for the concentration, or for the pressure of X, it's 0.55 minus N, and for Z, it's just going to be N. The Kp expression, we already know the Kp expression is the partial pressure of Z over the partial pressure of X. So it's going to be N over 0.55 minus N. And we know that the Kp expression is, got to go up, 3.3 times 10 to the negative 8th. So let's write that down. 3.3 times 10 to the negative 8th equals N over 0.55 minus N. From here, we just have to solve for N. What do we, kind of got lost in the sauce. What are we solving for? The partial pressure of compound Z at equilibrium, which does equal N. So we're just solving for N at this point. The algebra isn't too bad here. I'm still going to go to my graphing calculator because I'm just a little bit lazy like that. So 3.3 times 10 to the negative 8th. And then for my y2, I'm going to do n divided by, or x divided by 0.55 minus x. What I'm doing is I'm graphing both of these in my graphing calculator. This is y1, this is y2, and I'm going to solve for where my graph for y1 intercepts my graph for y2 because that's what n has to be equal to. And the answer is 1.815, or just 1.8 rounded to 2 sig figs, times 10 to the negative 8. And the units are going to be in ATM. That is my answer. The other way you could have done this, we already have talked about K being really, really small. What that means is that like the change of X is pretty much negligible. This reaction does not really progress that much in this direction. It's a wicked small K. So what that means is we're going to end up with so much more X than we are Z at equilibrium. So what we can say and what we can assume, and this is kind of the AP Chem intended way, is we can just say that 0.55 minus n is equal to 0.55. And when we do that, then the denominator becomes 0.55, and that becomes way easier to manage because then you're just doing 3.3 times 10 to the negative 8th times 0.55, and you get the same answer. So it's a good assumption to make because that's such a small K, to say that the starting pressure is going to be equal to the final pressure because it doesn't really progress. But I like to use the graphing calculator. And you know what? Let's just leave a little message to the AP grader saying that that's how I found this answer using my graphing calculator. A sample is compressed to half the original volume without any change in temperature. Does the value of Kp increase, decrease, or remain the same? K is going to remain the same. K only changes when we have a change in temperature, and we're specifically told there is no change in temperature. Q, we'll get a Q. What's going to happen if we increase the volume, if we compress the volume, then the pressures will change, and that will lead to a Q, and we can find how it's going to reach its K. But the K itself does not change here. K only changes with temperature. All right, continuing on. In the reverse reaction, the conversion of compound Z to compound X is catalyzed, and in the presence of trace, my goodness, everything's just popping up, of trace amounts of water. The catalyzed reaction is proposed to occur via the following two-step mechanism. Identify the intermediate in the mechanism, if any. There is an intermediate. That intermediate is Y. Y. We don't need to explain why it's Y because it doesn't say. So intermediate is Y. But the reason it's the intermediate is because it gets produced and then consumed in a subsequent step. A reaction profile of the uncatalyzed reaction is shown on the same axes. Sketch a reaction profile consistent with the proposed mechanism for the catalyzed reaction. So it's a two-step mechanism, and what catalysts do is they decrease activation energy. So it should be something like this. Same starting point, two-step mechanism, same ending point. Something like that should be good. Let me make that a little nicer. Something like that. Ooh, and the first step is the slow step, which I did accidentally, but make sure that first step is a little higher than that second step. All right, we're moving on to the second FRQ. Yeah, we're moving on to the second FRQ. Write the balanced chemical equation for the dissolution of calcium hydroxide in pure water. CaOH2 solid turns into Ca2 plus aqueous plus 2OH minus aqueous. Dissolution equations, they're not that bad, but you got to know how to do them. But that's a point. You do not need the states to earn the point for this question. Calculate the molar solubility of calcium hydroxide in 0.1 molar calcium nitrate. So we are going to do a Rice table here. Rice tables are how we determine our solubility. There's my R. I just need my I, my C, and my E. So this is a Rice table, but not for something dissolving in pure distilled water. So we're still going to have 0 of OH at the beginning, but we're going to have 0.1 molar calcium nitrate because we have that calcium ion in there. So this is going to have to do with the common ion effect. So we're going to go plus S, plus 2S, and then my E column is going to be 0.1 plus S, and then we get 2S for my OH minus. I should have made this smaller. I'm running out of room. Put that there. My K expression, my KSP, is going to be equal to the concentration of the calcium ion times the concentration of the hydroxide ion squared. So I get that KSP is equal to 0.1 plus S times 2S squared. Now we need the KSP, and I realized I cropped this thing pretty badly because I missed one of the lines where it tells me where the KSP is. So right above here, it says that the KSP is equal to 1.3 times 10 to the negative 6. I don't know what my thing is. My pen is glitching out a lot. Yeah, it's like just stopping at some points. It's annoying. 1.3 times 10 to the negative 6, so now we can go back and we can calculate that. So 1.3 times 10 to the negative 6 equals 0.1 plus S, and then 2S squared. All right, so once again, we reached a point. We can plug this into our graphing calculators to solve for S for us. If we make this y1, if we make this y2, and then solve for the intercept. The other way we can do this is, again, looking at the KSP. That's a very, very, very small KSP. It's times 10 to the negative 6, which means calcium hydroxide isn't really that soluble. So what we can say is, since we have some initial calcium nitrate, we can say that that initial concentration of calcium nitrate is going to be pretty much the same as the final concentration of calcium nitrate, because it's not going to dissolve that much. So what we can say is that the final concentration of the calcium ion is just going to equal 0.1. We're making the assumption that 0.1 plus S equals 0.1. So that turns that to this, and that makes this question a whole lot better algebraically to solve for. If we do that, so we do 1.3 times 10 to the negative 6th divided by 0.1. I'm going to do some algebra in my head, distribute this square, divide that by 4, and then square root that answer. We get that S is equal to 0.0018 molar. That is the solubility. And it's a pretty good assumption to make. If we did this via graphing, you'd get something pretty similar, if not the exact same to that. Lastly, in the box below, complete a particle representation diagram that includes 4 water molecules in proper orientation, and it tells us how to draw the water molecule. Water has a positive and negative end. The hydrogen ends are the positive end. The oxygen end is the negative end. This is a cation, which means we want to point to the negative end of the water molecule towards the cation. And we need 4 of them. It's going to look like that. And then they're going to form these ion dipole forces between the water molecules and the cation. All right, I believe that is it. So that was the FRQ. 2 rice tables in there, but overall, a lot of, I felt like, pretty relatively easy stuff, but from previous units. So make sure you're remembering to brush up on those previous units. There's a lot of material in AP Chemistry, and it can get overwhelming if you were just cramming until the very last moment every time. Make sure you're going back and you're looking at some of this other stuff because it will show up in FRQs. All right, that is it for this one. Good luck in the rest of your studies, everyone. And that is it for me. I'll get this video up. I actually got to go run to the hospital because my godson was just born. So that's my plans for the rest of the night. So if you message me this weekend, I probably won't answer. All right, bye.